This time what we're going to do is we're given a plane in general form and we're given an external point from this plane. Well, we'll find out if the distance is 0, that means it was in the plane. That would be a mistake, or maybe not. A dirty trick though, that would be mean. I'm going to assume there's an external point in a plane given in general form, and what we want is the distance from that. So the first thing I'm going to do as usual is draw a picture. M's over there, and then what we're going to have is a plane down here, P. So I want to find the distance. The distance, first of all, is the shortest distance from 2 points is going to be, in particularly the point in here and there, is going to be the perpendicular dropped from this. So I know that what I want is this guy. This will be our distance. So how am I going to use our machinery of vectors and that kind of stuff to find this distance d that we want? This is the distance. So what we're going to do is first we're going to pick an arbitrary point. We don't know where that point lies, and that's what we want. We don't know where it lies. So what we're going to instead do is we're going to create the normal vector to the plane, which they've already given us. It's the coefficient standing in front of x, y, z in the general equation. So we already have the normal equation to this plane. We've got n. So that will be useful. What we do is we construct n, and then all the vectors that are in the same direction, remember, and have the same magnitude are all equal to n. So then we can move n anywhere in the plane and make it go through m now, because they're all equal to n, the vector n. If they have, two vectors are equal if they have the same direction and the same magnitude. So that now I can put n through m on here, and I know n is perpendicular to the plane. What I now need is an arbitrary point n, say, in my plane, so that I can create another vector. And what we're going to do is, once we create this vector, I'm going to create this vector because Mark did it like this. So what we're going to do is create that vector, and then we're going to orthogonally project it onto here, and that will be the projection of the vector v we're going to create onto n. Then the length of that is exactly d. The vector we're going to create, v, is going to be equal to mn, which as vectors is n minus m. Where do we get those? Well, I needed to point n on there. Cleverly, coincidentally, how do we do that? The best way to do this, and I'll use the same one that from the problem that I stole this from. If I set two of these guys, I need a point that satisfies this equation. A lot of time the easiest way to do that, if you don't want to be clever, is kill two, let two of them be 0 and solve for the third guy. And it's one equation and one unknown, coincidentally. So if I set x equals 0 and y equals 0, that says 2z minus 2 equals 0, or z equals 1. So we get the point n now is the point 0, 0, 1, who happens to be the vector k. But either way, this is equal to now 0, 0, 1 minus the m, which we have, which is 3, negative 1, 5, which is equal to negative 3, positive 1, and negative 4. Once I have this vector now, this is my vector v, remember? And what else do I need? I need the vector n from the general form of the plane. Now we have, I'll make you remember too if you forgot, given the general equation of a plane, the normal vector to that plane is the coefficient standing in front of the variables. So n is equal to 2, negative 1, 2. And now we've created our vector v, which is negative 3, 1, negative 4. The next step is we need the projection of v onto n. So the projection of v onto n as a vector is equal to v dot product with n over the norm of n squared times n. And coincidentally, d now, we might as well simplify this calculation cleverly, because d is in fact the magnitude of that projection of v onto n. And then if we do this using some clever algebra, you'll see what's in some of the textbooks as the final formula. We're essentially deriving it, but here you go. Once I do this, this is just a number v dot n, but I have to take it out in absolute value, so that's v dot n. Then I see that this is now the norm of n over the norm of n squared. This is the norm because we're taking norms again. Now one of those cancels and we get the norm of v dot n in absolute value, because the distance has to be positive. So if that dot product is negative and the angle is obtuse, we're still going to get a positive distance now, but over the norm of n, which in coordinates, if you want, is going to be, usually we call n a b c, and v x naught, y naught, z naught, and then you're going to get v dot n, and then the norm of this guy's square root of a squared plus b squared plus c squared. That's where they're getting the formula. Since we have that, now you see that to compute the distance, essentially, if you just want to memorize, the distance from an external point to a plane is the absolute value of v dot n over the norm of n. V was created from the external point to a point in the plane. N was the normal vector. That's all you need. Now let's compute v dot n. Let's do these as side calculations. Basically what we're going to do is I need v dot product with n is going to be -3, 1, -4, dot product with 2, -1, 2, which is equal to -3 times 2 plus 1 times -1 plus -4 times 2. I see specifically it is negative, so the angle is obtuse, which is -6 minus 1 minus 8, which is -15. And then I need the norm of n. The norm of n is equal to the square root of 2 squared plus -1 squared plus 2 squared, which is 4 plus 4 is 8 plus 1 is 9. The square root of 9 is 3. So this tells me that the distance is the absolute value of -15 over 3, which is 5. This is the distance between the point and the plane. Quickly to recap again, if you're doing this for the first time, what do you need? This calculation, you can look at this again. I'll draw the scenario again to explain what's happening one more time after I drink coffee. What happened? This is the calculation you need. So on the exam when you're going in, the distance between an external point and a plane is, you need to find the absolute value of v dot n over the norm of n. Who are these people? Let's recall one more time. So I need the normal vector n. Usually in the plane, it's already given to you in the problem. So n was already there, I have it. That's who you need, n. 2, -1, 2. They gave it to me in the problem. Then what do I need? That can be through the, and then any one of those vectors is all equal, so I just move it till it's through the external point that they gave me. Then I need a point in my plane. That's the vector v. Then we're orthogonally projecting v onto n and then taking the norm of that, and the clever simplification is, once we do that, is this will be v dot n over the norm of n will be the distance between them in absolute value. So this is the distance. Who are the pieces? V comes from creating that vector from a point in the plane and the external point, and n is the normal vector usually given in the general form to start with. I was supposed to keep it short. Make easier problems, Mark.